Over 1 million Hawaii residents and visitors were thrown into an absolute panic when an individual at the Hawaii Emergency Management Agency pressed the wrong button on the ballistic missile warning broadcast system, sending out a false missile warning message. Now you might be thinking that that sounds like a really straightforward event caused by some human pressing the wrong button. What an idiot. Typical human error. Someone needs to be fired. Now, of course, a lot of people seem to think that this is clearly a case of human error because the media tells us every day that between 60 and 90% of accidents are caused by human error. Now, I'm going to show you that it's a little bit more complicated than that, and that this event was not simply a case of so-called human error, and anyone saying that it is simply human error and pointing fingers are missing a really important perspective. I'm going to show you a different view, an overview of a preliminary cast accident analysis that I've put together of this event. I intend that by the end of this video, your view about this event and so-called human error will have changed. I also intend to plant a seed in your mind so that you want to learn more about the cast accident analysis method. Overall, I think this particular event is a blessing in disguise, and we should take this golden opportunity to learn as much as we can from it. Hello everybody, I'm Simon Whiteley. In this video I'm going to talk about the now infamous false missile warning that occurred in Hawaii on Saturday the 13th of January 2018. I will give you an overview of a preliminary cast accident analysis that I've done for this event based on currently available information. Then I'll talk about my observations, and then I'll highlight a few questions that I would ask if I was part of the investigation team. I will make some specific observations about one of the changes rapidly implemented by the Hawaii Emergency Management Agency in the aftermath of the event. I don't consider that change to have solved the immediate issues and may have actually introduced new safety issues which need to be addressed as a matter of urgency. As a system safety engineer, I think this event and the subsequent aftermath is very significant and could spark a change across the world and really bring system safety and human factors to the forefront of everybody's mind. If you like this video, please click the like button and share it with your friends and colleagues. For those of you who don't know who I am, I'm Simon Whiteley. I'm a system safety engineering consultant from the UK. I've worked as a system safety engineer across all parts of the engineering and product lifecycle across a number of industries, predominantly aerospace and defence, including working on large aircraft, fast jets, helicopters, jet engines, missile command and control systems, missiles, ordnance, munitions and explosives, and air traffic control. Now, I'm particularly interested in the use of the stamp-based safety assessment methods, of which cast accident analysis is just one of those. And this is because I believe the methods are going to revolutionise the way we design, develop and operate safety-related systems in the future. It's early days and I'm doing my best to spread the message and help others. So you might be wondering, what is cast accident analysis? Well, very simply, CAST is an accident analysis method born out of MIT and the work of Professor Nancy Leveson and her team. CAST is an acronym that stands for Causal Analysis Using Systems Theory, and CAST is based on systems and control theory principles. It is a model-based analysis method and is different from other traditional accident analysis methods in some important ways, which I'm not going to go into in any detail in this video because I'd like to keep this video as short as I can. CAST is a relatively little known method that is very powerful and presents a way to analyse accidents and incidents and identify causal scenarios that need fixing. So what happened? What was the event? Well, essentially, Hawaii residents received an emergency notification at 8:07 Saturday morning, warning of an inbound ballistic missile threat and urging them to seek shelter. The warning message was sent out to over 1 million people across Hawaii via mobile phones, TV and radio, and this resulted in absolute panic and distress amongst the population. In reality, there was no missile threat and the warning message was actually false and sent by mistake. The organisation that sent the message, the Hawaii Emergency Management Agency, later sent out a second false alarm message as soon as possible afterwards. Overall, it took 38 minutes before the false alarm message was sent. initial investigations highlighted that an individual operator pressed the wrong button on the message broadcast system. To provide some context surrounding this event, during 2017, North Korea began firing a number of ballistic missiles, and naturally there was an increase in tensions between the US and North Korea. And this prompted the Hawaiian authorities to activate the nuclear attack warning system for the first time since the Cold War. And this involves, amongst other things, a monthly test of the sirens. Now, as part of this activation, the Hawaii Emergency Management Agency began preparing procedures and drills so that they could, when necessary, rapidly broadcast a message warning of an incoming missile. To rapidly broadcast a message obviously requires a team working 24/7 across 3 different shifts per day in a purpose-equipped facility called the State Warning Point. And the teams essentially sit there waiting for the incoming missile threat from the US military, poised to act as rapidly as possible. Now, because of the proximity of Hawaii to North Korea, it only takes about 20 minutes from launch to impact, and the military need 5 minutes to confirm the threat and the target. So, for example, Guam, Hawaii, or the mainland United States. Now, in that 5 minutes, the United States Pacific Command, US PACOM, the Federal Emergency Management Agency, FEMA, and the Department of Homeland Security, DHS, they conduct what's called a missile event conference. And it's after this that PACOM then notify the Hawaii Emergency Management Agency at the State Warning Point. Once this message has been received, the State Warning Point then begins the process of alerting Hawaii to the threat. And it's important to recognise that this whole process of threat assessment and emergency message notification has to be done as quickly as possible to give everybody as much time to get to shelter as possible. So this means that in a real event, people might only get 12 to 13 minutes warning, and in that time they must take immediate action to get to shelter. Now, it's in this context that the Hawaii Emergency Management Agency has spent the last few months, since November 2017, preparing to deal with this threat so that they could give as much notification and preparation time as possible. And this is essentially a focus on designing, implementing and operating a high-performance system, people, processes, procedures, training and technology in the best way the people involved know how. So let's talk about the system objectives. What is the system that we're talking about, and what is its prime objective or purpose? Well, first, let me just quickly define system in my simple language. I'm referring to the whole system, what's called the social technical system. So that means the people, the processes, the organisations, the technology, the communications, the hardware and software, the whole thing, not just the technical parts. So the system in this case is the alert and warning system, and it's intended to warn the population of Hawaii about ballistic missile threats in sufficient time such that they can take appropriate action, and this is done by broadcasting what is called a civil danger warning message. Now, Hawaii is an island community, and that presents some quite significant challenges and threats in its own rights. So the warning system is also intended to warn the population of other threats to life and property. Things like natural, accidental or man-made disasters, including tsunamis, hurricanes and volcanoes. Now, it's important to understand and appreciate that the warning system was only recently modified to include the missile threat warning, and that was about November 2017. So what we're looking at here is a period of change, modification, transition and testing, and coming up to speed. And this kind of period is typically when most teething problems occur, including accidents and incidents. So it should almost be expected that something is going to happen during times of change or disturbance. So what was the actual accident? What were the outcomes that we're interested in? Well, because it's early days since the event, reports are still coming in as to what's actually happened as a result of the false warning. I'm aware of a report that a man suffered a massive heart attack brought on by the terrifying false alarm. He flatlined for 5 minutes before receiving life-saving emergency surgery to put 4 stents into his heart. Fortunately, he survived, but I don't know whether any other people have been injured or have died as a result of this event. It's certainly very clear that people were understandably severely distressed and panicked. I'm also aware that the 911 emergency services telephone lines were jammed by worried people, and that also the mobile phone and internet data networks suffered some performance and availability issues. I don't know of any property damage or losses or the scale of any economic damage or loss, and it's not clear yet whether there has been any impact on the perception of Hawaii as a safe place to visit by potential tourists. It's also important to recognise the potential damage to the trust and support of government authorities, as well as the perception of their integrity and competence, and of course the public's trust in the messages provided by the warning system. Now let's talk about the hazards involved in this particular event. What we're interested in from a system safety perspective is essentially two main system states. The first is whether there is a valid missile attack threat, and the second is whether a warning message has actually been broadcasted. So using standard functional safety guide words, we consider whether a function is provided or not provided, or the timing or sequence is early, late, or in the wrong order, or if the magnitude is too much or too little. So for this particular event, and for keeping this video short, we're only really interested in whether the function is provided or not provided. So the first hazard or safety related scenario to think about is that a message is not sent when a missile threat is valid, and we really don't want that to happen. We want to make sure that a message gets out every time and as fast as possible, and to as many people as possible. And it's really clear from listening to the initial press conference that the Emergency Management Agency staff members were very much focused on that scenario, as you'd naturally expect. And then the second hazard to think about is that a message is sent when a missile threat is not valid. And this is exactly what happened in this particular event, and is what I'm focusing on in this video. Now, it's important to understand that when we design a system, when anybody designs a system or changes a system, it's really important to think of not only what we want the system to do, you know, the reason why the system exists in the first place, its primary purpose, but also those things that we really don't want to happen, like send a warning message when there is no threat, or accidentally launch a missile or crash two aeroplanes into each other. And this is the main challenge that system safety engineers get involved in. They essentially have to hunt down those subtle but significant nasty scenarios and then do something about them. And for me, that's what makes me passionate about system safety engineering, but also about the stamp-based methods, because they give you a powerful ability to see and deal with things that other more traditional safety analysis and accident investigation methods simply cannot. So let's talk about the high-level safety constraints. These are the safety constraints or requirements that the system design, the real as-built operational system, must enforce. And in the language of the CAST accident analysis method, these constraints are what the hierarchical control structure, HCS, is intended to enforce. The high-level safety constraints are essentially transposed from the hazards that we're interested in. So the first one is, the control structure shall ensure that a message is sent when a missile threat is valid. And the second is, the control structure shall ensure that a message is not sent when a missile threat is not valid. Clearly, in this case, the second safety constraint was the one that was not adequately enforced by the system design. And so we need to look into why that was the case. And that's essentially the purpose of a CAST accident analysis, to establish why the control structure did not enforce safety constraints. Now obviously there are a few other safety constraints that can be derived related to message and response timing, for example, but I'd like to keep this video as short as I can. Right, okay, so now I'm going to talk about the hierarchical control structure models, or HCS models, on the board behind me. Essentially, these are pictures or models of the hierarchical control structure that I've created based on the publicly available information in the media, press releases and press conferences. The HCS models form the basis for the CAST accident analysis. Now I've created two, a simple abstract control structure to highlight the context, and then a more detailed specific control structure which I'll then walk through and describe the sequence of events. This is a simple high-level abstract control structure which represents the overall system relevant to this particular event. On the left hand side we've got a hostile adversary and their ballistic missile, the threat. Then we've got the US military and their ballistic missile defense system. And then on the right hand side we've got what's called the alerting authority, in control of broadcasting a message to the general public, and then of course the general public who are in control of their daily life. So this whole control structure basically represents the whole system in a very simple abstract model. Now the ballistic missile defense system essentially has two primary functions. One is threat detection and assessment, and then the second is threat engagement. And so the function most relevant to our cast accident analysis is the threat detection and assessment, and then how the outcome of that is passed quickly to the alerting authority for their onward broadcast. Now obviously in this particular event, and as far as I'm aware, based on available credible information, recognising that there have been a few conspiracy videos on YouTube, there was no real ballistic missile threat, and so there would not have been a message sent by the US military to the alerting authority that would have prompted them to broadcast a real warning message. So the cast accident analysis and the modelling of the control structure basically focuses on this part of the simple high-level abstract control structure, on the alerting authority, broadcasting a message to the general public causing panic and distress. This is a more detailed control structure model, and it represents the overall system relevant to this particular event and the focus of my analysis. I've essentially expanded the model to provide more detail of the system components and their interactions so that they can be examined as part of a cast accident analysis. Now it may be that I have missed a few things or misinterpreted the source information in some way. I'm not an expert on this system or its architecture. But of course, if I was doing a real cast accident analysis, as opposed to an example like this, I'd obviously be working with subject matter experts so we can be sure to capture appropriate detail in the control structure model before we do the analysis. So on the left hand side we've got the US military, who would send a warning message if there is a missile threat to the alerting authority. Here I've expanded the alerting authority component to highlight the Hawaii Emergency Management Agency aspects, including the organisational and human aspects, as well as the technical aspects, and have labelled the technical parts of the broadcast system as the technical broadcast system. So we've got the state warning point crew and their message broadcast procedures, and they interface with what I've called the technical broadcast system, and that incorporates the human machine interface, or HMI, the so-called IPAWS compliant CAP alert origination tool, which allows the crew to basically broadcast a message across these different channels. Now IPAWS stands for Integrated Public Alert and Warning System, and CAP stands for Common Alerting Protocol Standards. So we've got various broadcast channels. We've got the Emergency Alert System, or EAS, which is the system that broadcasts messages to radio, cable and satellite TV. Then we've got the Wireless Emergency Alerts, or WEA, which broadcasts to the cellular mobile phone networks. Then we've got broadcast to various internet services, and then broadcast to various unique alerting systems, so things like the sirens and the digital signage at the side of the road. The intent of this whole system is to get an alert from the US military to the public as fast as possible, and so this whole structure, this whole system design is intended to be high performance. It's supposed to move quickly, and so the people in the state warning point, they will be trained and probably drill pretty much every day to make sure that they can issue this message as fast as possible so that the public have enough time to take cover and potentially save thousands of lives. Every second in delay in a real scenario will cost lives, and it's really important to understand that any high-performance rapid response system has some form of tension between being able to respond fast when required and the potential for false alarms. It's an inevitable part of system design and architecture which has to be carefully engineered, especially if the result of not responding or being late is so severe, as in this case. In some cases, we may have to accept a certain level of false alerting in exchange for the system to be high performance. So really, we should consider the perspective that whilst the system responded falsely, this is probably better than if it was not to respond at all or in time in a real scenario. So now I'm going to go into the timeline itself and talk about the sequence of events and what happened at what time on the morning of Saturday the 13th of January. At 8:05, the state warning point was going through a crew shift change. As part of preparing a shift change, the incoming crew perform a drill or practice test of the incoming ballistic missile preparation checklist. At 8:07, during the drill, a state warning point crew member pressed the real warning message button, PACOM CDW state only, instead of the practice warning message button, drill PACOM CDW state only. And after selecting the wrong option, the crew member then hit yes on a second confirmation page that asked if they were sure they wanted to broadcast the selected message. Once the second confirmation was given, the real warning message was broadcast to over 1 million residents, triggering a statewide panic. At 8:10, the state warning point crew received the real warning message on their mobile phones via the wireless emergency alert system. They also received phone calls from the director of the Hawaii Emergency Management Agency, General Logan, and the agency administrator Vern Miyagi requesting confirmation that the message was real or false. General Logan then contacted Pacific Command, who confirmed that there was no missile threat. It was after this point that the state warning point crew began taking action to stop the warning message broadcast and began attempting to recover the situation by sending out a false warning message. At 8:13, the broadcast cancellation command was issued, which prevents any further warning messages from being broadcast. To be clear, the broadcast cancellation command doesn't send out a separate cancellation message. All it does is stop the process of broadcasting the warning message. At 8:20, the Emergency Management Agency issued a public notification of no missile threat, false alarm via Facebook and Twitter. Between 8:24 and 8:30, Governor Ige also issued public notification via Facebook and Twitter. At 8:45, and after the state warning point crew received authorization from the FEMA IPAWS team, they issued a false alarm message, and it was at this point most members of the public received the false alarm message via their mobile phones. So overall, from initiation to notification of a false alarm, the event lasted about 38 minutes. It's important to understand that the various system components in this control structure each have their own view of the world, or what's called their mental model or process model. And these models influence component behaviour, which is based on what's called the control algorithm. So when a broadcast message is received, it updates their mental models, and then each component responds with specific behaviour defined by their control algorithm. For most people, because they didn't know what to do, their control algorithm was inadequately defined, and because the prospect of being vaporised and not seeing their loved ones again was deeply distressing, they began to panic. A proportion of them began a frantic search for information by calling the 911 emergency services line, friends and family, or by searching the internet. And this behaviour caused problems for the telephone and mobile phone networks, as well as internet websites. Others who were prepared, who had an adequately defined control algorithm, began to take action. Now, it's important to appreciate that because each component in the control structure has its own version of the truth contained in its mental model, and it can control its own behaviour, it is critically important that their mental models are in sync with other parts of the system and that their control algorithms are adequately defined. Otherwise, this can lead to unsafe or disruptive behaviour, which could make the situation even worse. And to add to that, if a message is received by components that are involved in other safety-related activity, such as car drivers, air traffic controllers or pilots, it's important to consider the impacts upon their behaviour and the knock-on consequences. So when designing any system, and certainly before commissioning or operations, a system safety assessment should be done so that all of these aspects are considered and adequately addressed. Now, I'm not convinced that a robust system safety assessment was completed prior to this event based on what I've seen, so I must recommend that a formal system safety assessment be performed and the requirements enforced, such as ensure the public and visitors know what to do and why. I highly recommend performing the stamp-based safety assessment method called STPA, or Systems Theoretic Process Analysis. Regarding the state warning point crew, technical broadcast system and the human-machine interface between them. As far as I understand it, the state warning point crew create and broadcast messages in accordance with their broadcast procedures using a computer-based system known as IPAWS, or the Integrated Public Alert and Warning System. So for a message to be broadcast via IPAWS, the crew use some software referred to as an IPAWS compliant CAP alert origination tool. Bit of a mouthful. This photo, released to the media, shows the human-machine interface of this tool. Essentially, when a message is intended to be broadcast, the user selects a pre-formatted and pre-authorized message from the list, and then the IPAWS tool sends this message to what's called the IPAWS Open Gateway for onward broadcast via the various communication channels. Now in this picture you can see the basic architecture of the IPAWS system. Now you'll notice that this slide refers to FEMA, and this is because IPAWS Open is essentially under the control of FEMA, and so if a new message needs to be broadcast through IPAWS, as I understand it, the message template needs to be created and be compliant with the Common Alerting Protocol standards, the CAP standards, and the message template then needs to be authorised by FEMA for broadcast across IPAWS. The message template creation, validation and authorisation process will, of course, take some time to do, especially where coordination is needed between the Hawaii Emergency Management Agency and FEMA staff members. And I suspect that this is the source of most of the delay between cancelling the warning message broadcast and then broadcasting what was effectively a brand new message. So there are lots of interesting topics here. It's an absolute goldmine of learning, but I'm only going to touch on a few topics to keep this video as short as I can. The first and most obvious topic is the human-machine interface and software development aspects of the IPAWS alert origination tool, coupled with the message template creation process. So from the HMI screenshot, it's clear that there were some obvious issues with the software's human-machine interface design, message template naming convention, and message template ordering and grouping. Message template names were not distinct, there was no clear ordering, grouping, or obvious cues as to the serious nature of each of the templates or of the associated behaviour of the broadcast system, whether it's a simple test broadcast or a broadcast to millions of people. The two-step "Are you sure you want to do this?" confirmation was also a completely inadequate safeguard to prevent unintentional message broadcasts. So these basic issues suggest that the template creation process and the software behaviour and functionality were not fit for purpose. It was inevitable that at some point the wrong message would be broadcast. It was essentially an accident waiting to happen. In fact, I wouldn't be surprised if accidentally sending the wrong message hasn't happened many times before amongst other organisations using the IPAWS software, not just the Hawaii Emergency Management Agency. So if I was an investigator, one of the recommendations I would make is to go looking for other events amongst the entire user community to understand how widespread this is and what could be done about it. And this is something that the Federal Communications Commission, FCC, should go looking for as part of their separate investigation. Clearly this event cannot be blamed on simple so-called human error. As I said at the beginning of the video, it's more complicated than that and not the fault of an individual person. The issues highlighted imply that the software tool designer and the creator of the message templates did not adequately consider system safety engineering or human factors aspects. So it's imperative that a system safety and human factors assessment is performed looking at the software HMI and the message creation procedure, and that their contribution to the hazards and accidents is identified and that changes are made to adequately control or eliminate their contributions. I also recommend that an overall assessment of the message broadcast system is performed so as to identify any other system safety and human factors issues that also need to be resolved. Now you might be wondering, how and why could this happen? Well, it could be anyone's guess, but I wouldn't be surprised if any of the following reasons applied. Number one, it could be that the warning system was not developed in accordance with appropriate standards. So for example, in the case of the military part of the control structure, they would develop systems in accordance with military standards which explicitly include requirements for system safety and human factors to be addressed. whereas the civil part of the control structure may not be required to use similar standards. Number 2. It could be that the potential for sending the wrong broadcast message was not identified, or by doing a risk assessment it was assumed that the probability was so low that it could be ignored. Number 3. It could be that the software supplier believed that the software couldn't kill people or cause harm because it's only part of a simple broadcast system. Number 4. It could be that the software wasn't identified as safety related in the concept or design stage. Number 5. Or it could be that efforts to identify and fulfill system safety and human factors requirements were inadequate or completely overlooked. Number 6. Or that it was agreed in the contract for supply of the software that it was not safety related, ignorant of the actual reality. Number 7. Or it could have been that the organisation that set the contract for supply of the software did not set adequate system safety or human factors requirements in the first place, probably presuming a competent supplier would adequately deal with those aspects. Now obviously my list of reasons isn't exhaustive and some sound like a bit of a joke, but in reality these reasons are dangerously common and should be recognised and resolved. So if you want to protect yourselves and your customers or the public, get some system safety, software safety and human factors engineers deployed on your projects, and fast. Now I won't go into the massive topic of software safety, so-called software failure, probability of software failures and risk assessments in this video because I want to keep it short. But it is an increasingly common challenge that I don't think is being taken seriously or even recognised by the majority of organisations using or developing complex software systems. Another significant topic is with regards to the message broadcast procedures, the training and drill practice design, personnel numbers and organisational structure, and the original so-called system change, i.e. the introduction of the missile warning message to the alert and warning system in the first place. So this prompts a number of questions. So why was the training and drill practice designed such that a warning message could be sent incorrectly? What controls were put in place and why didn't they work? Why didn't a false alarm message and associated broadcast recovery process not exist prior to this event? Was it because the alert and warning system change process to introduce the missile warning message did not consider any kind of system safety assessment or human factors analysis? These questions seriously prompt the recommendation to perform a system safety and human factors assessment of the changes to introduce the missile warning message, and identify their contribution to the identified hazards and accidents and make changes to adequately control or eliminate their contribution. And I would highly recommend that the stamp-based safety assessment method, STPA, is used for that assessment. And this leads me on to talk about one of the changes that were made in the immediate aftermath of the event. The change I'm referring to is the change that requires 2 people to check before the message is sent via iPause. No real detail has been provided, so it's difficult to get a clear understanding of how the process worked before and how it works now. So I'm making a few implicit assumptions, but essentially if you don't change the software, procedure or drill practice and only add an extra person, you may well appear to reduce the likelihood of an inadvertent message broadcast, but it doesn't actually eliminate the potential and doesn't address the other systematic factors, which could also trip up 2 people just as easy as it does 1 person. It's important to appreciate that regardless of the 2-person configuration, both of those individuals must share the same mental model and may well suffer from the same software, HMI and human factors issues as a single person. So let me be clear, asking people to be extra careful and to check each other's work doesn't solve the systematic problems. Building on what I said earlier about the software HMI design requiring a system safety and human factors assessment, I recommend that the changes to the team organisational structure and interactions, as well as their procedures for real and drill practice, need also be carefully considered and redesigned. So now I'd like to touch briefly on cybersecurity and the potential for a cyber attack. During the first press conference held by the Hawaii Emergency Management Agency, it was commented that there was no hacking or other cybersecurity aspects to this event. It was all purely human error, a mistake. Now, the first thing that springs to mind for me is, how could they know for certain that this was the case unless they'd actually checked first? You know, what cybersecurity investigation had been done less than 2 hours after the event occurred? The second thing that springs to mind is, what if the software was compromised such that the button the individual thought they were pressing was actually linked to a different unwanted behaviour that was invisible to the individual? Does North Korea have the capability to do this? Do other adversaries? It's certainly something that I would look at, especially given that the broadcast system directly affects the hearts and minds of the enemy and does not need shots to be fired. Again, I recommend another stamp-based method called STPA-SEC, or Systems Theoretic Process Analysis Security, to be used to assess this aspect. Now I'd like to talk about the blame game, death threats and so-called second victims. I admit sometimes it's important to have a bit of fun and laugh serious things off, perhaps even with a bit of dark humour. But when it results in pointing fingers, immediately blaming people, or mocking individuals for being stupid or incompetent, it really makes my blood boil. Now, I recognise and understand that it's a natural human response to seek a reason and assign blame, but we all must do our best to manage that response, otherwise we're potentially damaging the ability to learn and prevent future accidents. So if you know someone who is prone to jump into conclusions, pointing fingers, blaming or mocking individuals involved in an accident for being stupid or incompetent, please help them open their mind a little bit by helping them to understand that people don't typically intend to make mistakes and cause an accident. They're doing the best they can given the circumstances, what they know and what they can control, and they typically have your best interests at heart. However, if the system that they are a part of is set up to conspire against them, how is pointing fingers, laughing, or even threatening them going to help deal with such a significant event? Most people would feel threatened, closed down, and wouldn't want to speak about what happened. Now, I'm aware of reports that the person involved in sending the broadcast message has been sent death threats. I'm also aware that that individual has reportedly refused to cooperate with the investigation. So how is that going to help the investigation to understand what happened and how, so we can learn to prevent future accidents? Well, the simple answer is it's not. So what does it mean if we can't do an adequate investigation and make changes? Well, it means that this accident could happen again and more people are going to get hurt or even killed. And all of this negativity also really doesn't help those who are aggrieved or who lost their loved ones. It also doesn't help when the media hounds those involved to get a story and often misrepresent the situation. In some cases, blame has led to suicide and even murder, as in the case of the air traffic controller who was involved in the Überlingen air disaster over Germany in July 2002. He was murdered by a desperately aggrieved father who lost his wife and 2 children aboard flight 2937. You know, this was a desperately sad air accident underscored by another desperately sad death. Now, Sidney Dekker talks about so-called second victims or people involved in accidents in his book Second Victim. I recommend buying a copy and reading it. Sidney has written some great books. Please look him up. But please don't get me wrong, I'm not trying to promote a no-blame culture. I'm merely trying to help people understand a bit more about themselves so that together we can take the pressure off those involved in an accident so that an effective investigation can be done to prevent future accidents and to minimise further suffering. If you'd like to learn more about the CAST accident analysis method or the other stamp-based assessment methods, I recommend buying a copy of Nancy Leveson's book Engineering a Safer World. You can get a free PDF copy of the book. I've included a link in the description, so please take a look at that. I'm also putting together an online training program for CAST accident analysis, so if you'd like to pre-register your interest for that, please click the link in the description and I'll be sure to let you know when it's ready for launch. As I mentioned earlier on, I recommend reading Sidney Dekker's books about human factors and particularly the book Second Victim, and of course the now legendary book by Donald Norman, The Design of Everyday Things, where he talks about some of the human factors aspects that were involved in this particular accident. Ultimately, at the end of the day, conclusions of human error basically mean that the investigation was not finished and that the opportunity to prevent the same or similar accidents from occurring again has been lost. What we need to do, and what we must do, is understand the social technical system that humans form a part of and how that system, its components and interactions, including human behaviour, conspired to result in an accident. This is the prime objective of the CAST accident analysis method and why it's so powerful in identifying causes of accidents and opportunities for prevention. So what do you think? What do you think to what I've said? Has it sparked some interest or raised some questions in your mind? Do you still think this event is a case of simple human error, a simple mistake? Do you still think it's all to do with the user experience or human-machine interface? I'm hoping that what I've shown you and what I've said has sparked some thoughts and ideas and may well have changed your viewpoint. So if you have any thoughts, comments, questions, ideas, I'd love to see them. So please type them in the comment box below and let's start a conversation. If you like the video, please click the like button, share it with your friends and colleagues, and of course subscribe to my YouTube channel. You can also follow me on Twitter and connect with me on LinkedIn. Thanks very much for watching. I'll see you on the next video. Good night.